Okay, welcome. I put the lecture notes online, so if you want to go to Blackboard, you can see there's a variety of PDF files there. And I already mentioned in the last class meeting that I've radically reorganized this class compared to some previous semesters. And so I may do some additional tweaking to the lecture notes in terms of what comes where. But for the most part, I think things are stable enough that I wanted to push it out to you so you've got it available. The other thing that you'll find on Blackboard is the first homework assignment. Don't know why that didn't change from last time. Homework 1, Precipitation, is available now, and I'll show you a couple of websites today that you're going to need to access in order to solve that assignment. So definitely get an early start on that. It'll be due before class on Wednesday next week. So that's the 17th, yeah. So, any questions before we get into it? Okay, well, if I was going to give you a pop quiz today, which I'm not, but if I was giving you a pop quiz, the question would be, what drives the hydrologic cycle? Yeah.
Is it precipitation?
No. That's a good guess, though. It's before the precipitation. The sun. That's right. Yeah, the sun drives the hydrologic cycle because it's the sun that provides the energy that causes evaporation, condensation, precipitation, runoff. So it's the incoming solar radiation that drives that ongoing hydrologic cycle. Okay. So we're going to talk about a wide variety of things related to precipitation today. But before we do, I wanted to just give you the idea of what is a watershed, what is a basin or a catchment. These words are used interchangeably in a lot of ways, and when I took a hydrology course, the instructor was talking about watersheds, and I didn't really understand necessarily what he meant until maybe partway through the semester. And so a watershed could be something small, or it could be something big. And this is Google Earth Pro, which is a free program that you can get, and you're just looking at aerial maps. You can zoom in on places. One of the nice features, though, is that underneath Google Earth Pro, it knows the altitude of the land. So you'll notice one of the things down here at the bottom is it says elevation. Just because it's using a digital elevation model, it's draping the photo over a digital elevation model. So if you move the cursor back and forth, for example, you could trace a ridge line, just simply, you can kind of tell from the looks of it, like where the trees are thicker, where they're lighter, and so on. And you could use the elevation here to get a notion for the watershed. But another nice thing is that you can rotate and pivot, and because it has the altitude information in the background, you can kind of get a sense for where those boundaries are when you make a video of it. So can you tell that there's a ridge line there, and we're looking at a bit of a basin. And so when any raindrops fall in this basin, they're going to drain towards a common point. So here's one part of the basin, and here's another part of the basin. If we look over here to the side, so it looks like there's two segments, two branches that come together and lead through this person's yard. So it probably, when it rains hard, they're a little bit worried about that. But a watershed, we could say that this part of it is a watershed if maybe we were just interested in what's the flow rate from that single branch. Or a watershed could be the combination of these two branches together. And so the watershed is just dependent on your point of interest. So if you're trying to size a culvert that's going to carry the flow underneath a road, then maybe your location of interest is here. And if that's the watershed outlet, then the watershed is all of the area upstream that drains to that point. Or we could even get more macro, because there's going to be a stream that runs along Little Cabell Creek Road. And so the watershed, if that was my location of interest, would encompass a much larger area. So we're going to look at different ways to delineate those watersheds later on in the semester when we get to the watershed modeling portion of the course. But a watershed ends at one end of the watershed is the high elevation, the ridge line. And then at the other end of the watershed is just simply where all the water is draining to, and ultimately watersheds end at the ocean because that is the lowest point that water's draining to. But it's a nested hierarchy depending on if you're looking at a relatively small area and the limited branches of streams that feed into that. But within a large watershed are successively smaller watersheds that compose it. So how much water is coming out at the end of a watershed depends on its size, obviously. And so the bigger the contributing area, the more the flow is going to be. It also depends on what's inside of the watershed, how the land is being used. And one of the reasons why we have to be careful about human development is that when we add roadways and driveways and roofs, that all of those surfaces don't absorb water like the natural land that was there before it. So when a previously forested watershed is paved, then that's going to increase the runoff that goes downstream. So it can increase the runoff and threaten the buildings that in the past were totally fine maybe to build next to the river. But if the watershed upstream becomes developed, then the asphalt isn't going to hold on to water as well as forest litter would, for example. Soil conditions also have an effect because clay soils don't tend to absorb water as quickly as sandy and gravelly soils do. We'll talk about soil classifications later in the semester when we get into calculating infiltration. And then the conditions of the terrain, like how steep the slope is, can also contribute to how much water is infiltrated. And a very steep side slope that the water flows quickly over doesn't allow for water to penetrate down into the pores as quickly as if it's relatively flat. And then the rainfall conditions are all obviously going to contribute to how much runoff you get. If it's a really intense storm that happens quickly and kind of overwhelms the ground's ability to infiltrate water, sometimes storms will be focused only on one portion of a watershed compared to others. And so if there's a rainstorm at the far end of the watershed, it takes time for the flow to travel through the network compared to if the storm is closer to the outlet, then it can arrive much more quickly without the routing delay that otherwise would occur. So those are just kind of some signposting to give you a sense for perspective. You know, we're not talking about rainfall just for the sake of it's interesting, gee whiz, it's rainfall. We're trying to figure out what are the characteristics and trends that are related to runoff, because that's the engineering thing we're trying to do. Is there's going to be too much water that we need to dispose of somehow, and we need to know how much of that water there's going to be in order to size the infrastructure that can carry it away. So when we talk about precipitation, it's just within mind that what we're ultimately working towards is ways of estimating how much runoff is likely to come from an area of interest. Okay, so precipitation begins with air movement. And air movement on a global basis can be attributed to two big effects. And there are obviously different temperatures of air at different altitudes. If you've ever been on a plane that tells you the outside temperature as you're flying, some of the screens sometimes will tell you what altitude you're at and what's the outside air temperature. You'll know it's very cold aloft, that the air temperature decreases quite a lot from the ground level as you go upwards. And that's related to the fact that pressures are much lower in the upper atmosphere. There's a direct relationship between lower pressures and lower temperatures. Part of it is driven by the Earth's rotation and by temperature differences at the poles. So Hadley circulation is largely related to temperature differences at the poles. So think about if you have cold temperatures at the top and the bottom of the globe. And what we know about gases is that when they become cold, the air is more dense and it falls, compared to when air is heated, it expands and it rises. So think about at the equator, as the air is warming, what it's doing is it's rising. And you can kind of get a sense from this figure of that. You see that sideward arrow? That's kind of, it's just implying that the air is rising at the equators and it's falling at the poles. And what that does is it kind of sets up what you can think of as a belt. Now we're looking at a 2D cross-section where we've got the air falling at the poles, rising at the equators, and because it's going in those directions, it rises and then it goes through the upper atmosphere towards the poles in order to replace the air that has fallen, and then as it falls closer to the Earth's surface, it is kind of spreading out laterally. And you have to think about, as a globe, what this is like. The continuity principle just says that if a certain volume of air is extracted in one place, it has to be replaced at another. And so all of the air that's going down from the poles is replaced in the upper atmosphere. So it's just a matter of equatorial air rising. And then the other part of it, remember, is that the Earth isn't stationary, it's rotating. And the Earth is rotating more quickly on average than the gases above it. And so it sets up the combination between the Earth's rotation and her Hadley circulation together. Those two things together cause these typical airflow patterns that we're, for example, here in North America, accustomed to the wind bringing storms from the western United States towards the east. But it's not that way at every single place on Earth. That's just happens to be at our latitude that the winds are typically from the west towards the east. If we go further down south, like into Central America, then the trade wind direction at those spots is that the wind is coming from the east and going towards the west. So you can see in this animation here, it's just illustrating that if you have some stationary object, but it is moving, in this case you can see that the marble is moving down like the air would for the Hadley circulation. We know that the general trend is downward, but then the surface to which it's affixed is rotating. Then this is kind of showing the pattern of the wind being the trade winds at these mid-latitudes. And so in the southern hemisphere, it's kind of a mirror image of the northern hemisphere. But back in the early days, the 1700s, 1800s, they used these typical wind patterns to govern sea voyages and what direction they could count on wind taking them to cross the ocean and get from place to place. So these bulk air movements just are interesting to us in the sense that it gives us an idea of what direction the weather is going to be coming from, and then the proximity of land masses to these trade winds can also impact the likelihood of precipitation. So this helps to explain why there are deserts in certain locations, like the Sahara Desert. If you think about, it's right next to the ocean, so why is it a desert? It's because the Sahara is at the latitude that the trade winds are associated with, and so the winds are blowing from the land out to the sea. It's not the opposite direction. If it was blowing from the sea towards the land, then we might see a little more precipitation at that latitude. But those winds can carry water quite a bit further from where it actually evaporates. There was a study done some years ago where they radio labeled water and then tracked where it was detected, And so water that was released at this dark black cell here was detected pretty far away because the wind movement of the moisture as it had evaporated, and repeated the test in Asia and detected that that water pretty far away. And it's partly because of how widespread air movement is that people really worry when there's a nuclear accident in Japan or in Ukraine that that contamination could travel really far and affect people all over the world. So there's a story that we can think through on how rainfall begins. And this is something where I'm going to ask you on the exams to to describe a few things in your own words. They're going to be short answer concept questions, and one of them that seems to pop up almost every semester is explain how precipitation forms. And so let's walk through that process. The first step is that air needs to become cooled. And you've probably heard of the dew point before. If you watch the weather on TV, sometimes they'll talk about the dew point. Air has moisture in it. You've heard of relative humidity before. Even really dry air has a little bit of moisture in it. When I was living in the desert, sometimes we'd have humidity as low as 10 or 20%, but there's still some moisture in the air in the desert. So when the air cools, what that's doing is it increases the relative humidity of the air, because the solubility of water in air increases with temperature. If you think back to chemistry about what solubility is, for example, if you pour salt into water and stir it, there's a certain limit to how much salt can be dissolved in water. And in the similar way, there's a certain limit on how much moisture can be dissolved in air. And when you get above that limit, or at the limit, is 100% relative humidity. When you go above that limit, then condensation has to occur. And so air that is maybe 70% humidity at, let's say, pretty warm conditions, 85 degrees Fahrenheit. If it's 70% humid and 85 degrees Fahrenheit, if that air cools, then the humidity increases, because cool air can't hold as much moisture on an absolute basis as warm air can. And so if the quantity of moisture is fixed and the relative humidity is going up, eventually you'll get to the point where the air is fully saturated with moisture and it has to go somewhere else. So think about a can of Coke that you get out of the fridge. It's not sweaty when you get it out of the fridge, but when you set it on the desk, condensation occurs on the can because the air that's surrounding the can has moisture in it, and that thin layer of air that's very close to the outside edge of the can becomes saturated with air. It achieves the dew point around the can. And so the first step is that the air has to cool somehow. Something causes the air to cool, and the moisture content is getting closer to fully saturated. Now, there are some phenomena that cause minor amounts of cooling, like air can radiate its energy outward. There can be mixing with warm air and cool air that causes the air to cool off, conducting heat from the air to something like a building. So heat can flow from the air to other things, but most of the cooling that causes storms, so hydrologically significant means the cooling that's likely to cause precipitation, is when air is lifted up. That's the main thing that causes the air to cool off, is this recognition that we've seen that when you get high up in the air, it's really cold up there because of what's called the adiabatic lapse rate. Just the fact that air is expanding, and as it expands, it cools, and as it cools, the humidity increases. The relative humidity is going up, and it's getting closer and closer to the dew point. So just let's say there's some forces that cause the air to be lifted up, and as a certain volume of air is lifted up through the atmosphere, the relative humidity is increasing. And it gets to the point where the humidity is at 100%, the air is fully saturated with moisture, and so the excess moisture has to condense on some sort of a nuclei. It could be dust particles that's up in the atmosphere. It could be salt. Like in coastal areas, sometimes just salt spray from the waves crashing on the rocks. The little particles of salt get up into the atmosphere, and that's a condensation nuclei. And it could be other droplets of moisture that the water is condensing on. So our book has a series of diagrams to show that, for example, what's classified as dry fog is 10 microns or less. Fine mist is from 10 to 100. Fine drizzle from 100 to 300. And you'd notice it if you drove through on a really foggy day. If you drive through a fog bank, you'll sometimes notice it on your windshield, and you have to turn on the wiper. And you've probably noticed before light rain where it's not penetrating, but it just seems like the droplets are much smaller. And that can be if there's only a thin layer of clouds, and the clouds, if it's a thick layer, the thunderstorm, which is going to have big fat droplets of water, is where multiple small droplets have collided together and they've combined in size, and they begin to fall more quickly and get larger in diameter as they have collisions and increase in size. So excess moisture has condensed on a nuclei of some sort, and the droplets grow from collisions, and the water vapor continues to increase the size of droplets as they fall down through the atmosphere towards the ground. So, cooling of air through lifting. Vertical uplift is the main thing that causes air to cool off. If you climb up a mountain, you'll notice you can feel it, that it's cooler up above as you go up on the mountain. You can even actually notice it on buildings. I went on the Burj Khalifa over in Dubai, and at the ground level, it's probably about 5 or 6 degrees warmer than it is up above, because that's how tall the building is. It's tall enough that you actually notice the temperature difference. The adiabatic lapse rate is about 1 degree Celsius for every 100 meters of altitude. That's how much the temperature decreases because of the density of air. And as the density decreases as you go up through the atmosphere, the temperature decreases along with it. So some air packet that has, 80%, 90% humidity, as it is lifting and it is cooling, the relative humidity is going up. Now there's 3 main causes of uplift that contributes to the hydrologic significant precipitation. And you should memorize these terms. This is going to be on that vocabulary list that I give you, these 3 terms. Convergence, which means things coming together. Orography, which is air being lifted over a mountain. And then convection, which is air that's lifted due to daytime solar radiation. So those are the 3 main causes of uplift. Let's talk about each one of them individually. So the lapse rate that I told you of about 1 degree Celsius per 100 meters, that is for dry air. Moist air has a slightly lower lapse rate, and so if you have fully saturated air, then the decrease in temperature would only be about 0.65 degrees Celsius for every 100 meters of elevation. Dry air, you can see here it's saying 9.8 Celsius per kilometer, so that's about 1 degree per 100 meters. So air that is lifted cools off, and sometimes if you've ever looked at a weather map before, maybe you've seen, this is a top view. If you've seen like especially old-timey weather maps from like the 50s and 60s, before they had radar to show you, they had these sketched out diagrams that would show where there's locations of high pressure, low pressure, relatively warm and cool fronts. And so this diagram as a top view is just saying what happens when you have cold air approaching warm air. And that's going to happen to us this weekend. I was just looking, and I think it's supposed to get into single digits on Sunday night. So get ready for that. We've got relatively warm conditions now, and cold air is going to be approaching that. So you've got cold air, like maybe a cold wind is coming towards where it's been relatively warm for a while. Let's look at the side view of what happens in a case like that. So what happens as the cold air approaches, it pushes the warm air towards maybe another region that also had cool air. So this is like an encroaching pocket of warm air that's being pushed around by cold air, and it's being pushed towards a different area that's cooler. So if warm air is being pushed towards cool air, what happens is that it rises slowly over that cold pocket, and it says that it's associated with light, long duration precipitation. So a warm air converging on a cold front is going to cause slow day-long drizzle, it's saying, if a warm front is being slowly lifted on top of a cold front. But then when the cold front is approaching, it displaces the air up into the atmosphere very quickly, and it causes it to rise more fast, and the thunderstorm, which is the quick lifting of moisture, is associated with, here it says, heavy, short duration precipitation. So what you should know about convergence is just that there are fronts, meaning different temperature air masses coming together, and the warm air is being lifted up, the warm, moist air, because remember, warm air has the ability to hold more moisture than cool air does. So if cold air is lifted up through the atmosphere, the effect is less significant. Because it was cold to begin with, it wasn't likely to be carrying much moisture. But it's the warm air that's being lifted up through the atmosphere that causes the really significant precipitation, because if it was previously warm, that means it probably had more moisture dissolved in it. Okay, so that's convergence. And I'd encourage you to read through what the book has to say about each of these topics. We're just kind of scratching the top of the explanation, and there's a lot more to learn. The next force we're going to talk about is orography. And this is a top view of an island. I don't think that this is Hawaii, but Hawaii has very similar conditions that we'll look at in just a minute with a different map. But the wind direction at this location is that the wind blows from the sea and in the directions indicated by the arrows. So the windward side is the side of a mountain range that has the wind blowing towards it, and then the leeward side, this is a ridge line here. This is high altitude. So the wind comes from the ocean up over the mountain and then back down the mountain face. And so you can see here it's like a desert, and on the other side it's very lush. And it's not a difference because it's been sprayed with pesticide. It's not a difference of soil types. It's simply a difference that's related to how much precipitation there is at both of those locations. So what's happening, this cross-sectional side view gives you a sense that if you have wind that's being forced to rise in elevation to get up over an obstacle, the obstacle being the mountain, the wind, as it rises up over the mountain, is getting closer and closer to saturated. The amount of moisture that's in there is fixed, but the solubility is decreasing as the temperature goes down. And so it's getting closer to the dew point, and eventually, at a certain elevation, it's going to be fully saturated. Condensation will start to occur because the excess moisture has to go on to droplets. And so there's going to be an excess of moisture on the windward side, but then as this packet of air gets over the top, it's kind of exhausted all of its excess moisture. And especially because as the moisture goes down, as the air goes down the mountain, it's going to be warming up again. And so as the air is warming, it's getting further and further away from being fully saturated. So it's kind of like a double effect. You have a big reduction in the moisture content because you've exhausted all the precipitation on the windward side, and then on the leeward side, not only isn't there as much moisture, but then the air is warming up again and getting further and further away from fully saturated. So the leeward sides of mountains are much drier than the windward side. So that's orography. Looks like I have a video here, although I don't really remember what it is. Let's see. So you can visibly notice this orography effect in the west especially. You know, here in West Virginia, not as much because, for one thing, the mountains aren't as big as they are out in the west, but there's just more moisture to begin with, whereas in the western part of the United States, the relative humidity is usually pretty low to begin with, and so there's a big difference on one side of a mountain compared to the other. So here's a mean annual rainfall map for the island of Oahu. Anybody here ever been to Oahu before? Yeah? I've only been once. It was great. I can't believe I've never been back. You should definitely go on trips go to Oahu before you buy a nice car. It's way more important. Going on fun trips is way better than driving a nice car. Mainly because then you'd get to see stuff like precipitation patterns, and I've been on the leeward side of Oahu. It's like pretty low rent over on this side. You know, people think of Hawaii being lush and tropical. It is on this part, but over here, it's kind of like trailer park Hawaii. You know, it's like it's grim in certain parts, I guess. I saw some grim parts. I was surprised. I thought all of Hawaii was going to be a paradise, but that's not necessarily the case. So that's this is the effect of orography, is that air is lifted up over the mountains, and you can see that, look at the range of precipitation. You've got 5 meters of precipitation, 5,701 to 7,075. So 7 meters of precipitation in the year, which is, we're talking like 21 feet. That's a lot more precipitation than we get around here. And then 1/10 of that on the leeward side of the island. Okay, so we've talked about frontal lifting, which is convergence. We talked about orography, which is air moving up over an obstacle. And the third hydrologically significant source of lifting is convection. And so in the morning, the ground is cool because it cooled off all night. The sun is shining on the ground surface, and it starts to warm up the air that's close to the ground surface because the sun's rays are collecting on the ground. You know, like dirt is brown. It absorbs solar radiation really well. And so there's this heat that's rising, and it's got a lot of moisture in it. And as it's rising, then it's cooling, and it's getting closer to saturated. And if you've ever driven across the Midwest in the afternoon during the summer, you can see what looks like big mushroom clouds sometimes. I mean, it looks like what you've seen videos of nuclear explosions, but it's just the clouds. It's the cause of afternoon thunderstorms. You can really get into trouble if you're flying in the United States during the summer. It's better maybe to book your flight in the morning than the afternoon, because afternoon flights are a lot more likely to be canceled because of really intense thunderstorms. So this convective effect is just simply the daily cycle of the ground and the air cooling off at night and then as the sun is shining and over the course of the day building up more and more heat at the ground level, then that heat is transferred to the air, and the air is rising. So as the air is lifted, remember that it's cooling because of the adiabatic effect, and then it gets to a certain point where condensation occurs because it gets to the dew point, meaning fully saturated with moisture. The afternoon thunderstorm. All right. So this same effect occurs whether we're talking about rain or snow or hail. Hail is kind of an interesting case where the moisture is falling downward. It starts off as liquid, and it's falling downward through colder layers, because it's not always just a linear thing as getting colder and colder and colder as you go up. Sometimes there are inversions where you can have a layer of warm air between cold layers. And so hail occurs when a moisture droplet is falling downward and it goes through a freezing layer, but then it's blown back up again. And so it's kind of going up and down through this cycle of accumulating more precipitation on the outside of it through condensation and through impact with other liquid moisture, and then falling through the freezing layer. The dust particles that are in the air start off as negatively charged. And this is similar to water treatment, where if you've taken environmental engineering already, you maybe remember about how colloidal particles have to be destabilized with coagulants. And the coagulants suppress the negative charge that's on the outside of a clay particle in water. And the same thing is true with dust and salt droplets that are up in the air. Is they have repulsive charges where they won't really come into contact with each other as long as they have that repulsive charge. But as water coats the outside of a very small droplet, then the relative charge decreases, and it's more likely that there's going to be a collision and aggregation of the particles to become larger and increasingly big droplets that will fall downward. So that's kind of the theoretical story of, remember, if you were going to need to tell it in your own words, you've got warm, moist air that's lifted up, gets closer to the dew point, nucleation sites, causes the accumulation of moisture, and so it's just explaining what causes the lifting that's sometimes the tricky part. This is a map of the tri-state area. So here we've got Charleston, Ashland, Huntington, and each of these locations that are shaded in colors are rain gauges. It's kind of interesting how rare rain gauges are. You know, there are a handful of them in Huntington and Barbersville, but most of them don't have a long history of data. This figure, which comes from our textbook, shows you how many gauges there are that have a certain amount of years of data. So this is a logarithmic scale for a number of gauges. What this is saying is, in the entire United States, if you wanted to have 140 years of rainfall data, there's only 8 rain gauges that have continuous data of more than 140 years. 100 years we can do pretty well. You know, there's probably 250 rain gauges that have 100 years of data available. But think about it, the entire area of the United States, there's only 250 rain gauges that have a full 100 years worth of data. And why does this matter, 100 years of data? Well, we want to be able to design things so that they only fail for 15 minutes in 100 years or 15 minutes in 50 years. And so for us to be able to design up to the standard of a 100-year storm, we have to know how big is the 100-year storm. And if we don't have a rain gauge in our area that goes back 100 years, then it's just all statistical extrapolation. It's not direct measurement. So that's largely what we are dealing with, is statistically projected data based on a very small number of rain gauges across the United States. A hydrograph is a visual representation of either depth or intensity over time during a storm. So this is an intensity hydrograph, and you can see what it's showing is in 1 hour intervals, what was the storm intensity during a certain day. So during January 8th, the first hour of the storm, the rainfall intensity was about 1 inch an hour. Then it looks like it increased very slightly for the next hour, stayed constant through the third hour. The fourth hour was a little bit higher, then it dropped. So this is just averaging together in 1 hour intervals what was the intensity of the storm during that period. And what having a rainfall hydrograph can do is it can help you to see how storms vary from time to time. And just knowing the daily average, like if you know that there was in a 24-hour period 4 inches of rain, that doesn't necessarily tell the same story that this would with more temporal resolution. There's another way that we can express stormfall data, and that is as a cumulative figure. So you can see this first curve here is for January 8th, so it's the same storm, but this is more continuous, where we seem to have information almost on a minute-by-minute basis of how much rain was falling and when. So the steeper this line is, the more intense the storm is. And then you can see that on different dates there are other storms that have been offset. So this first axis for the time, 0, 60, 120, is related to January 6th. Then the next one below it, 0, 60, 120, 180, that's for the August 22nd storm. But we're not offsetting the y-axis here. In each case, we're just measuring how much accumulated rainfall there was in inches. So rather than being an intensity graph, the cumulative rainfall is telling you the total amount that fell for a certain storm. So the January 8th storm looks like it's nearly 5 inches, very close to 5 inches, but it's better for us to know when during January 8th that fell, because if we want to try and analyze how much runoff we observed, it's really helpful to know when was the rainfall that caused that runoff. So it's great when you have this kind of data available, but most of the time we don't, and we're going to be coming up with synthetic hydrographs. So we'll be synthesizing a temporal distribution based on just a total amount in a given period. So when I talk about rainfall amount, we can either talk about an amount of rainfall in terms of the volume of rain or the depth of rain that fell over a certain area. And so if you have a watershed catchment, let's say it's a parking lot. We've got a parking lot behind this building. If we know how much rainfall depth there is, and we know the area of the parking lot, then we can calculate the volume of rainfall. You know, if the parking lot is 5 acres and there's 3 inches of rain, then we could say that's 15 acre inches. And we could convert that from acre inches into cubic feet or into gallons, but it's just rainfall area expressed over, rainfall depth expressed over an area that you can get a volume from that. Volume is area times depth. And then rainfall sometimes is expressed in terms of its intensity over time. So measured that with inches per hour or millimeters per hour. And if you know the intensity of the storm and multiply that by the duration, then that would also give you the depth. Storms are sometimes described by their recurrence interval. And I spoke about this a little bit on Monday, how some storms which are very high intensity have a rare, limited occurrence on any given year. And so we can describe storms' size and intensity by how rarely they come along and how infrequent it is that we would see one of that size. So a 25-year storm is a pretty big storm because it's one that would only come around every 25 years, but a 100-year storm is that much bigger because it's more rare. Now, a 100-year storm is not 4 times as intense as a 25-year storm, not by any stretch of the imagination. We'll look at some actual recurrence interval storm data here in just a moment, and you'll see that a 100-year storm is only a little bit bigger than a 25-year storm. It's not a lot bigger. You know, we talked about frontal lifting, orography, convective storms. Those can cause a lot of rain, but the biggest storms are caused by hurricanes. In our area, we are under the influence of tropical storms, and the amount of water that will come in from a hurricane just absolutely dwarfs the precipitation you're likely to see from any of the other hydrologically significant lifting events. So here's just a screenshot that I got in 2018 of a storm that was going to hit North Carolina. And this is inches. They were expecting to see 35 inches of precipitation in Wilmington, North Carolina. And so that's like the entire annual precipitation that we'd normally get in West Virginia in a 24-hour period due to a hurricane. So there can be just unfathomable quantities of precipitation associated with tropical storms. IDF stands for intensity, duration, frequency. And so intensity of precipitation is how much depth per unit time there is. And that's the vertical axis on this curve. So you'll notice that it's a logarithmic scale. And so the rainfall intensity, this is showing for a certain duration storm. If we wanted to know a storm that comes around once every 2 years, so a 2-year storm, if we were interested in if it's going to last for a duration of 1 hour, we can go up, reflect off of the 2-year storm, and that says 1 inch per hour. So if you have a storm that lasts for 1 hour, you could expect that a 2-year storm would have an intensity of 1 inch per hour. The 100-year storm has an intensity of about 2.5 inches per hour for a 1 hour duration. It's these really short duration storms that we get the much larger intensities for. So they typically are governing for sizing of stormwater drains and parking lot inlets is the really short duration storms. The duration is just from the beginning of the storm event till its end, how long it's lasted in time. And the frequency is referring to the return period. So you can see this IDF curve has 100, 50, 25, 10, 5, and 2-year storm return periods. There have been these statistical extrapolations based on, there's not much direct measurement data available. Remember, maybe 250 storm gauges across the entire United States. Well, they've tried to determine what is this is the 2-year 60-minute precipitation depth. Hydro 35 is a product that's put together to kind of use what weather data we do have and come up with typical rainfall depths. Our book has these maps. It's got the 2-year, the 100-year, may also have the 25-year storm. But once you know one of those depths, you can determine the others through extrapolation. So if you know the 5-minute precipitation depth and the 15-minute precipitation depth, then you can use this averaging to determine the 10-minute depth. And also with the 15-minute depth and the 60, you can determine the 30-minute through like statistical extrapolation. And then there's also a table, an equation in our book that allows us to take the 2 and 100-year data and then find out what's the 5-year, the 10-year, the 25 and 50. So in the homework assignment that you've got to work on for Wednesday of next week, I ask you to go through and use these equations. So it's looking up some information from this map and then applying these equations to determine what is the precipitation depth for a 2-year storm, a 5-year storm, a 10-year storm, and so on. Okay, we're out of time for today. We're going to leave it here for now. We'll continue talking about precipitation in class on Friday.